So once again, welcome everyone. This is an exciting day. So my name is Christian Sasser. I'm the astronomer in charge for iTelescope. And today I have the pleasure to introduce to you a very prominent speaker from NASA, Dr. Jonathan Gardner. He's the Deputy Senior Project Scientist of the JWST, or if you like, the James Webb Space Telescope at the NASA Goddard Space Center. So Jonathan, please join me and let's give you a warm welcome. There you are. Hi, Jonathan. Hi, Dr. Gardner. How are you?
I'm fine, thank you, and I'm very happy to be here talking to you today.
Well, we are really pleased. We're so excited. I'm not going to talk about the James Webb because it's so exciting. I'm going to give the floor to you. So please go ahead, and it's all yours. And just let me know when you want to run the polls. Thank you.
Okay. I will. I'm going to share my screen. Okay. Are we live? Can you see it?
Yes.
All right.
Live. That's fine.
Thank you. So I'm going to be telling you about the James Webb Space Telescope. You might have heard of it before, but I'll tell you some details. James Webb is a 6.6 meter space telescope. It's the successor to the Hubble Space Telescope, not a replacement, I should say. It's the successor. Also the successor to the Spitzer Space Telescope, which was our previous infrared telescope. It's the first time NASA has used deployed optics in space, and I'll be showing you what that means. It's visible light and infrared optimized. It's passively cooled to 218 degrees below 0 Celsius. It was launched on Christmas Day of last year, and I hope some of you got to watch the launch. It is designed to be complementary to other telescopes, both on the ground and in space. If we can do something with some other telescope, we'll save our Webb time for things that only Webb can do. It's an international collaboration, a joint project of NASA, the European Space Agency, and the Canadian Space Agency. And in all, there were 14 countries that contributed to the mission. The lead within NASA is the Goddard Space Flight Center in Maryland, where I work. The prime contractor that built the observatory was Northrop Grumman Aerospace Systems. Operations is being conducted on the campus of Johns Hopkins University at the Space Telescope Science Institute, which also operates Hubble. And the senior project scientist is 2006 Nobel laureate John Mather, and I'm his deputy. So when we first started thinking about a successor to Hubble, the scientists involved organized the science goals of Webb around 4 science themes: finding the first galaxies that formed after the Big Bang, the evolution of those galaxies over time from how they started to present-day galaxies like our own Milky Way, the formation of stars and planets within our Milky Way, and planets and the conditions for life, both extrasolar planets or exoplanets and planets within our own solar system. So one of the very first things that we thought about was finding the first galaxies that formed in the early universe. And this picture, the Hubble Ultra Deep Field, is the faintest picture that humanity had ever taken before Webb. With the Hubble Space Telescope, about a month's worth of observation time and about a year out of the 30-year lifetime of Hubble has been spent doing follow-up observations in this field and around it. Now, what jumps out at you is the relatively bright or nearby galaxies. You can see a spiral structure, some elliptical galaxies. Almost everything in this image is a galaxy. There's only 1 or 2 foreground stars. But when you want to see the galaxies that formed in the early universe, you have to use your telescope as a time machine. You have to look backwards in time. And we do that by looking for things that are very far away, such that the light has traveled through the universe over most of the universe's history. And in the Hubble Ultra Deep Field, here's a few candidates that are at our what we call redshift beyond 6, or galaxies that we're seeing light that was emitted within the first 1 billion years after the Big Bang, where the Big Bang was 13.8 billion years ago. So the light from these galaxies has been traveling for almost 13 billion years. And when we look at these galaxies and study them in a bit more detail, we found that these are not the first galaxies that formed in this area, because some of them are already several hundred million years old. And so in order to find the first galaxies that formed out of the pristine hydrogen and helium from the Big Bang, we have to go still further. So how do we go still further than the faintest picture that Hubble can take? Well, we need a telescope that's bigger than Hubble, because we need to see things that on average are going to be fainter, collect more light, but also because as the light is traveling over the history of the universe is expanding, and that expansion stretches the wavelengths of the light. So light that's emitted in the ultraviolet with brand new hot stars, in the visible light, stars like our sun, is stretched out over this this passage through the universe, is stretched out and pushed into the infrared. So we need an infrared optimized telescope. And an infrared optimized telescope means that your telescope has to be very cold, because anything that is at room temperature will emit infrared light and swamp the signal from the distant galaxies. So in comparison, Hubble's primary mirror is 2.4 meters. That's just a little bit bigger than a tall person, whereas Webb's primary mirror is 6.5 meters or 6.6 meters from flat to flat. And in order to make a mirror this big, we had to make it in pieces. Hubble's mirror is a single piece of glass ground to the optical prescription, whereas Webb's mirror is made up of 18 individual primary mirror segments, each 1.3 meter hexagons. The segments are made of beryllium and coated with gold. Gold is very highly reflective in the infrared. Hubble is kept at about room temperature. One reason to do that is that we sent astronauts up to Hubble, and we didn't want them to freeze onto the telescope when they were working on it. But more importantly, Hubble is in low Earth orbit, and it goes in and out of sunlight every 90 minutes. Whereas, it gets heated by the sun and then cooled off when it's on the night side of the Earth, and heated up again. So we keep Hubble at a constant temperature using heaters, and we keep it at about room temperature to maintain the stability. Hubble also in its orbit goes between the Earth and the sun. So a single sun shield, like I'm going to show you for Webb, would not protect it from both. Webb, however, has a 5-layer tennis court-sized sun shield. It's made of kapton, which is a fairly thin plastic material coated in reflective surface, and will radiate its energy, its heat, into deep space, such that the primary mirror is at as cold as 55 Kelvin, 55 degrees above absolute zero. It's minus 218 Celsius or minus 361 Fahrenheit. And there's the sun shield before we put it on anything. And then finally, the difference between Hubble and Webb is the orbit. Hubble, as I said, is in low Earth orbit, 375 miles above the surface, 600 kilometers. That's as high as the space shuttle ever flew to launch and to boost Hubble's orbit, was the highest that the space shuttle flew. We sent Webb out to a special orbit called the second Lagrange point, which is 1 million miles or 1.5 million kilometers from the Earth, 4 times the distance of the moon. And it's a special orbit worked out by the mathematician, astronomer, physicist Lagrange a couple of centuries ago, in which the sun, the Earth, and the L2 point always stay in a line. So the Earth goes around the sun once per year. L2 goes around the Earth once per year, and those exactly match such that the sun, Earth, and L2 stay lined up. Webb is in orbit around the L2 point, and the sun and the Earth are on the hot side of the sun shield. The moon, our moon as well, is always on the hot side of the sun shield, and so neither sunlight, Earthlight, or moonlight can land on the Webb telescope. Now, when we decided we needed a large infrared space telescope to look for the first galaxies that formed in the early universe, we very quickly realized that that was also going to be very powerful for the other science themes of Webb, such as the formation of stars and their planets within our own galaxy. This is the iconic Eagle Nebula picture taken by Hubble as seen in visible light, and you see dusty clouds within which stars are forming. When you go to the infrared, you start to see through the dust and into where the action is happening. And if we go even further into the infrared, we would see down to where the forming stars, the protostars and protoplanetary systems are actually forming. So Webb is going to be very powerful at the study of stars and their planetary systems. And then finally, over the 25 years that I've been working on Webb, exoplanets have gone from a new discovery to an extremely important part of astronomy. And we will be using Webb to study planets around other stars, exoplanets, and planets in the outer solar system of our own solar system. The TRAPPIST-1 system includes 7 small, probably rocky planets that are transiting in front of their star. Now, a transit means that by a chance alignment, the planet is going between the surface of its host star and our telescope. And when that happens, light from the star is going through the atmosphere of the planet to reach our telescope, and we can just subtract off the starlight that happens outside of the transit from what we see within the transit, and we can actually measure the constituents of the atmospheres of exoplanets in a way that we can't do through trying to directly detect these planets. Now, in the lower left, you see a transit of the moon across the face of the sun. And if this picture were taken from the Earth, we would call this a solar eclipse, and the apparent size of the moon and the sun would be the same. However, this video was not taken from Earth. It was taken from one of our sun-observing satellites, the Stereo mission, that just happened to catch the transit of the moon across the face of the sun. But this is a good illustration of what happens when we have planetary transits. And then finally, within our own solar system, because of our sun shield, we cannot point Webb at Mercury, Venus, the Earth, or the moon, but we can observe Mars, Jupiter, and Saturn in some of our instrument modes. Taking a picture of these very bright objects would mostly just be saturated as fast as we can read out the telescopes, but we can observe it in some of our spectroscopic modes. And then the outer solar system, Webb is very good at studying Uranus, Neptune, moons of the outer solar system, Kuiper belt objects, also known as dwarf planets like Pluto, asteroids, and comets. And the outer solar system, it holds some of the pristine material out of which our own solar system formed. And by studying that, we can learn again about our history, about origins. So if you'd like to run the first poll about the science goals, you could do that now.
Okay, we'll do that. So
Okay.
the question is, which of Webb's science goals are you most excited about? The early universe, galaxies over time, star life cycle, other worlds, or I like the technology?
Okay, so I'm going to show you some of that technology for the people that want to choose the last one. This is a picture of a family portrait of our 4 cameras. We call this the Integrated Science Instrument Module because the 4 cameras share some of their systems. This whole thing is about 2 meters on a side, so it's pretty big, 2 to 3 meters, and we have the near-infrared camera right in the middle. That's the camera that takes the shorter wavelength infrared pictures and is kind of the workhorse imager, taking a lot of the pictures that you will see from Webb. The near-infrared spectrograph is a contribution from the European Space Agency, and it takes the near-infrared light and spreads it out into a spectrum where we can measure the velocity of the targets. And also, since individual individual atoms or molecules will emit light at certain wavelengths, we can see in the spectra, we can see a spike where the signature of that atom or molecule is, and that will tell us about the composition of the objects. One thing that's very fun for the people who like the technology in the near spec is we have a MEMS-based microshutter array. So MEMS stands for micro electromechanical systems. It's basically moving parts on a computer chip, silicon chip, and our microshutter array has 250,000 individual windows that we can open where there's a target of interest and close the ones nearby to cut down on the background or overlap of the spectra. Very cool technology. The FGS or NIRISS is our Canadian instrument. The guider is a fine guidance system, locks onto a nearby star to keep the telescope pointed perfectly at our target. But the Canadians also wanted to have a science instrument. So on the back side of the optical bench, they added the NIRISS, which is a specialized instrument designed to do basically 3 tasks. One is studying transiting exoplanets. Second is finding distant galaxies with spectroscopy. And then the third one is an interferometric mode that looks for planets or disks that are very close to a bright object like a star. And then last but not least, the mid-infrared instrument does both imaging and spectroscopy at the longest wavelengths that Webb can see. And so overall, to tell you what the wavelengths are, Webb can see light as short as 0.6 micrometers wavelength. That's gold-colored visible light. It is set both by our detector technology and the fact that our mirrors are coated in gold and absorb everything bluer than that. And it goes out to 28 microns, which is light that is emitted by very cold things that are tens of degrees above absolute zero. So as I said, this is a time-lapse video of assembling the primary mirror. So we had 18 primary mirror segments, and we had to assemble them onto the backplane in the clean room at the Goddard Space Flight Center where I work, using this robotic arm and a whole lot of technicians running around underneath to make sure everything got lined up properly. And we assembled the 18 mirrors onto the backplane. They were first put on with these protective black covers to protect it during this process. But then we took those covers off and we had the full gold mirror, primary mirror of Webb. And so this is a picture taken in the clean room with some of the technicians who you saw in the video. And one of the very cool things about this picture is that the photographer lined up the primary mirror with the NASA logo on the back wall. And what you can see very clearly in this picture is that Webb is not a flat mirror. It's got an optical prescription. It's magnifying and distorting the image of the NASA logo. You can actually, if you look at it, you can actually see the curvature. There are 18 mirror segments, and they have 3 different optical prescriptions because of the 6-fold symmetry. And there was a point at which the Webb primary mirror with the side wings folded back was visible from the viewing window into this clean room. And I got to take the coolest selfie I will ever take in my life. This is a picture of myself reflected in the Webb primary mirror. And I had to go all the way over to the edge of the viewing window with the curtain behind me to take this picture. They don't let scientists go in the clean room. That's only for the highly skilled technicians that are working on the technology. When we had the telescope and the instruments all assembled together, we then took it to the Johnson Space Center in Houston, Texas, for an optical test at the operating temperature. For this test, we used a historic vacuum chamber called Chamber A. Chamber A is 12 meters in diameter and 35 meters high. It was built in the 1960s for the Apollo program, and they tested the Apollo capsule inside this chamber. And in addition, it is human rated, and the astronauts, the Apollo astronauts, practiced walking on the moon inside their spacesuits in vacuum inside this chamber before they went on their lunar mission. So about 10 years ago, Webb took over this chamber, took out the simulated lunar surface, and installed a helium shroud, a liquid helium shroud inside to bring it down to the operating temperature of Webb, and put Webb through a 3-month optical test. Took about a month for it to cool down to the operating temperature. There was a month of taking data, test data, to make sure that the instruments in the telescope work together, and then a month to cool up, warm back up. And during that month, Hurricane Harvey came through and dumped 55 inches of water on the Houston area. There was massive flooding. The people working this test heroically kept the Webb hardware safe in the vacuum chamber and did not have to break the vacuum and thus either endanger the equipment or spend another whole month cooling down. So there's Webb has kind of been through a lot of adversity before it got to orbit, but that was one of the things, and a lot of people were putting in working under some pretty scary conditions. When we had the telescope and instruments ready to go and the spacecraft and sun shield, we assembled them together at the Northrop Grumman facility in Los Angeles. And here you can see the assembly together of the telescope onto the sun shield. That was then followed by a test of deploying the sun shield. Now, deploying the sun shield in a test environment, you have to offload it for the gravity because the actual deployment in space happened in 0G. You could see the pulling out the sun shield and then separating the 5 layers. And again, the sun shield is the size of a singles tennis court, and the 5 layers are about a foot, about a third of a meter apart. There's a picture of the final assembled telescope with the deployed sun shield. And I just put this picture in. I like this because it kind of shows you the scale of what it means to have a 6.5 meter telescope in comparison to the person there on the left. So then we packed it up last summer, ready for shipping to the launch site. And shipping actually went by boat. The MN Colibri, which carries the European Space Agency launches to the launch site in Kourou, French Guiana, South America. So the launch on the Ariane 5 rocket was provided by the European Space Agency. And the JWST did actually go through the Panama Canal, as you can see in the lower left, transitioning one of the locks. Then we got to the launch site, and the picture on the left is the last view that we had of Webb before it was sealed into the rocket fairing, as you can see on the right.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, stop.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So that was last Christmas and the launch of Webb. I love watching that again. I like the fact that because it's a French rocket, they count down in French. Then half an hour later, we got this view of Webb going off towards the L2 point with a camera from the fairing of the rocket. You can see in the upper right is the east coast of Africa with the Gulf of Aden there, and Webb going off on its way. This is the last high-resolution view of Webb that we will have. If you have a very large amateur telescope, small university telescope, you can detect Webb. It's something like 17th to 18th magnitude. In the control room, people were happy at the launch, but half an hour later, when we saw this, the solar panels popping out like this and deploying, that's when the control room went crazy, because we had done a rehearsal where the solar panel didn't come out, and everybody there knew that without the solar panel, we had 7 hours before the mission would have been lost. Solar panel deployed perfectly. It came out automatically about a minute and a half after fairing separation. And like everything I will be telling you about in commissioning, things just have went very well. So the 2 weeks after launch, we had 50 major deployments, all of which were successful. 178 release mechanisms, every single one worked. Solar panel was deployed and is providing nominal power. High gain antenna was deployed, turned on, and is currently in use. And our mid-course corrections and station keeping were all successful. In all, with a near perfect launch and mid-course corrections going very well. We have fuel for station keeping and angular momentum management for more than 20 years lifetime of Webb. That's the one thing that we use up over time. The deployment of the Sun Shield included 140 release mechanisms, 70 hinge assemblies, 8 deployment motors, 400 pulleys, 90 cables totaling 400 meters. Everything worked perfectly. If even one of those 140 release mechanisms had not released, we would have torn the Sun Shield on the way out and would be dealing with a degraded mission. But everything worked perfectly, separating the layers. And then we deployed the telescope, the secondary mirror. There's an instrument radiator on the back, and then the 2 side wings of the primary mirror. Those were the last of the major deployments. We then spent the next 2 weeks up to launch plus 1 month, moving each of the primary mirror segments off of the launch snubbers about 1.2 centimeters each. And moving those segments, we would do them kind of 1 millimeter at a time across the telescope. Turns out that it's literally slower than grass grows over those 2 weeks. The next step was to line up the mirrors so that they worked as a single telescope, a single optical surface. Each of the primary mirrors and the secondary mirror has 6 actuators on the back, so we can control their position with X and Y, where they are, Up and down, that's focus. We can tip them, we can tilt them, and we can rotate them. That's 6. And then there's a 7th actuator on the primary mirror segments to poke the back in the middle and adjust the radius of curvature. In all, there's 132 different degrees of freedom to align up the mirror. And we had to align the mirror to a total wavefront error, total position relative across the mirror of 150 nanometers, which is shorter than the wavelength of light. To put that in perspective, we had the primary mirror segments. If the whole telescope, Webb telescope, were the size of the United States, each of these mirror segments would be the size of the state of Texas, and we would have to line them up relative to each other to within 1.5 inches. So we then pointed the telescope at a bright star to identify where the telescope segments were, individual segments were pointed. We identified each of the 18 mirror segments by moving each one a little bit, one by one, to see what happens to the image. And this was our first picture of the sky where we could identify each of the 18 mirror segments. We then moved those points. Remember, this is all just one star, 18 different images, some of them pretty far out of focus of this one star. We moved them into a hexagonal array to kind of keep track of it. And then we went through a process of lining up or focusing each individual mirror segment and also bringing the secondary mirror into its optimal positioning relative to those segments. So each of those 18 images became a sharp 1.3 meter mirror. We then started stacking them up, lining them, putting them all on top of each other. This is not yet working as a single telescope. It's 18 individual telescopes, just all stacked up on top of each other. And this is the image we got. So this has the resolution or diffraction limit of a 1.3 meter telescope with the collecting area of the full JWST 6.6 meter telescope. Next step was to line up the mirror segments to each other within a fraction of a wavelength. We did this with an interferometric technique called a dispersed Hartmann sensor, and you can see the fringes getting longer and longer as the mirrors come close to where they need to be relative to each other. Final step uses weak lenses to take the telescope out of focus in each direction, which we can then analyze the data and see where the mirror segments are to do the fine phasing. This last step is a thing that we will continue throughout the lifetime of the mission. As the mirrors drift a little bit away from each other, we can tweak it back up and keep it all working as a single mirror. We take these data every 2 to 3 days, and we will actually move the primary mirror segments when we need to. Up till now, it's been every 2 to 3 weeks. This was the first fully phased picture that we took. There's a bright star, and one of the things that will become a theme for Webb images is that you can't point Webb anywhere on the sky without seeing lots of background galaxies. Webb is very, very good at detecting galaxies. They're everywhere. They photobombed this alignment image, and it should not have been a surprise to us, but it turned out it kind of was, because the telescope people were simulating the image of the star and didn't think about the galaxies. The scientists were simulating the images of galaxies and didn't kind of realize that this would show up in our engineering data as well. But there we have it. And of course, this didn't just happen automatically. There's a very hardworking team at the Mission Operations Center and around the world. In this picture, Dr. John Mather, the senior project scientist, is in the upper left, and then I'm a couple of people over from him. This was the team looking at the first images. We then took a picture within the Large Magellanic Cloud of a field with each of the 4 instruments and the guider, kind of in position of where they are on the field of view of the telescope. And one of the things that kind of jumps out is a comparison of Webb with the previous infrared telescope, the Spitzer Space Telescope. This shows what you get when you go from a 0.8 meter diameter telescope to a 6.5 meter telescope. You just really, it opens up a huge amount of what scientists call discovery space, area for new discoveries. This is a technical picture showing the current mirror temperatures of the primary mirror. It's actually quite a bit of variation. They're all a little bit, the warmest one is a little bit below 55 Kelvin, but the secondary mirror is actually at 29 Kelvin, 25 degrees colder than that. It doesn't matter that there's a temperature gradient across the face of the mirror, because beryllium has a very low coefficient of thermal expansion at cryogenic temperatures, so keeps its shape no matter what the temperature is. And then on July 12th, we brought out the first pictures, the Webb's first images. Also, we called these the early release observations. If you want to do your poll, see what people like in these. The early release observations were done with a total of 5 days of observing time, and the targets were chosen to demonstrate the capabilities of Webb. Demonstrate, at least at the level of what are the kinds of data we can get, what is the big advantage of Webb over the previous missions and other telescopes. I'm going to zoom in a little bit on some of these images and talk about them. First, we have a transiting exoplanet, WASP 96b. This is a Jupiter-sized, or about half Jupiter-sized object. I think it's what's called a hot Jupiter because it's very close to its host star. And it's actually about half the mass of Jupiter, but about the full size of Jupiter. It's a lower density because it's warm. And with this transiting technique, we were able to measure the atmosphere of the planet and detect a number of lines coming from water vapor in the atmosphere of the planet. This is just a hint of what we can do with exoplanets. And I mentioned the TRAPPIST-1 system earlier, where we would be looking at smaller planets that have a hard surface like the Earth, and potentially atmospheres with water and clouds. And there are, I think, 2 of those 7 planets are the right distance from their star, that if they have water on the surface, it would be liquid water like the Earth has, and not frozen water like Mars has, or water vapor like would be in hotter planets' atmospheres like this WASP 96b. This is, I think, is one of the most visually stunning pictures within the Carina Nebula in the Large Magellanic Cloud. This is a star-forming region, and the redder or brown is the dust out of which planets would be forming. But the filters were chosen to pull out forming stars as yellow in this image. And if you look deep within the cloud, you can see some of the yellow. Okay, seeing the results of the poll, looks like it's pretty closely evenly divided. That's interesting. Everybody has, all of the pictures have bands. So the yellow objects are the forming stars. And if we zoom in a little bit to a couple of places. So on the lower left, we've got one of these forming protostars. And forming a star and its planetary systems can be a kind of a messy process. The gas collapses to the center and forms the star. The dust collapses into a disk and then forms the planet. But there's a lot of angular momentum that needs to go somewhere. And sometimes that can create jets that shoot out the poles of the forming star. And so what we see down in the lower right is some of these jets coming from the forming star going off to the lower right and interacting with the cloud. And one of the things that's very cool is that a previous ejection from the star has made it all the way across the image to the upper right. And you can see the yellow blob in the upper left, that was ejected from this star along the line of the poles. Looking at Stephan's quintet, this is a group of 5 galaxies, of which 4 galaxies are in the same place and are interacting with each other. The galaxy at the left is actually a foreground galaxy, much closer than the other 4, and is not associated with them except visually on the sky. That's something that astronomers always have to worry about. It's hard to measure how far away something is unless it's extragalactic outside of our galaxy, and we can use the Hubble law, the expansion of the universe, to measure how far away something is. But anyway, so the 4 galaxies on the right are interacting, and the 2 down in the middle especially have gone through a very recent interaction, but this galaxy at the top is kind of colliding with these 2 as well. And the thing that the filters that were chosen in the mid-infrared bring out a feature of a dust feature that is associated with new star formation called polycyclic aromatic hydrocarbons. Just part of the process of forming stars will form that type of dust. And so with the interaction between these 3 galaxies, we see a band of star formation that jumps out in the mid-infrared to show where the galaxies are actually colliding. Now, when galaxies collide, they don't go bang the way cars would. They kind of slosh together and mix up, because most of the distance between the stars within the galaxies is very empty. And stars will very rarely hit each other directly because it's mostly empty space. But they interact gravitationally, and the gas does hit each other and create shocks, which can cause collapse into new stars. So here we have the combined near-infrared and mid-infrared image, and then just the mid-infrared, where we see the nice band of PAH dust associated with star formation. We see the same thing in the Cartwheel galaxy, which was released a little bit later. It was taken to be part of the early release observations, the first 5, but it didn't make the cut. So we just brought it out. We've got a couple more in our pocket to bring out in the coming weeks like this. And then we expect some of the first science results that scientists are doing to come out after that. Again, we see these dust lanes showing up in the red from the mid-infrared. And then the last one I'm going to show you is the galaxy cluster. This was the deepest infrared picture we have taken so far, a record that is soon to fall as we go through our first year of Webb observations. It was just 2 hours and 15 minutes per filter, or a total of about 12 hours of observations to take this picture, and already is deeper than the Hubble Ultra Deep Field in the infrared. And a couple of things that are nice about this picture. One is that it's a galaxy cluster, so it's full of dark matter, and that dark matter is bending the light from the background galaxies, in some cases magnifying that light, kind of focusing it on our view, and in other cases stretching out the galaxies into these long red arcs of again boosting the light using the gravity of the dark matter as a lens. So this we took this picture, and we also followed it up with the microshutter array on the NIRSpec instrument, and took this spectrum of a galaxy that is at a redshift of 8.5. That means the light has been traveling for 13.1 billion years. This isn't the most distant known galaxy, although it's by far the most distant galaxy for which we have such a nice spectrum. And again, coming up, we're going to have a whole lot more data like this, because the microshutter array can take multiple spectra at once. But when I saw this spectrum, and this is my favorite of the early release observations, this spectrum, which shows such a wealth of lines at a redshift of 8.5. We've got all of these hydrogen lines, but it also shows oxygen and neon. And what this tells us is that 700 million years after the Big Bang, we're seeing, Webb can see galaxies with a whole lot of detail. But because oxygen and neon are second generation elements, they don't come from the Big Bang itself. They're formed in stars that go through their lifetimes and blow up as supernova, get redistributed into the interstellar medium, and then incorporated into the second generation stars. This is still not a first generation star. We need to look even more distant to find the first generations of galaxies. But when I saw what Webb could do in just the first 5 days of observations, this told me that we're going to meet our science goals. But this was the first 5 days, and we started taking the first year of science programs about 6 weeks ago. So we have 8 times as much data as those first 5 days already. The science programs on Webb are selected through a peer-reviewed competition on an annual basis. And to kick things off, we included 13 early release science programs and front-loaded them to be done within the first 3 months. The EROs, the early release observations that you saw, were to show the public and everybody what Webb can do. These early release science programs are meant to show the scientists what Webb can do by providing actual data that scientists can download and play with. And these data are all available in the archive. If you have the right software tools, you can get them too and look at Webb data. The 13 programs range from deep fields, cosmological galaxy surveys, to gravitational lensing, nearby galaxies, astrochemistry in star-forming regions, exoplanet atmospheres, direct detection of exoplanets, and an in-depth study of Jupiter and its moons. So it kind of covers all aspects of astronomy, and several of these programs already have data, and there are already dozens of scientific papers analyzing the data that have been submitted to the journals. If you would like to follow along on Webb, of course, we have websites. We have a blog that provides some more in-depth information about what's going on with Webb. There's an image archive. And then, of course, we are on social media, and you can get the latest updates from the Webb project. So that's what I've prepared, and I'd like to thank you for attending today. And I